So let's talk about what Nash equilibria can look like for games with imperfect information. That is extensive form games that have information sets. So in general, Nash equilibria is still going to be defined the same way via a normalization procedure where we turn an extensive form game into a normal form game. And then we say, what are the Nash equilibria of the normal form game? But there's a subtlety, because when we take the normal form of a game of imperfect information, we need to use the fixed definition of strategies. So the normal form is going to have fewer strategies than it would if it was a perfect information game. So as is to say, we take moves for the player in the normalization are going to be kind of valid strategies for the imperfect information game. Okay, and then after that, everything stays the same. So we're going to define a pure Nash equilibrium to be a pure strategy Nash equilibrium of the normal form. And we can also define mixed strategy Nash equilibria the same way, and everything checks out because, again, it's a condition on tuples of pure tuples of strategies for each player. So everything works out. So let's work out an example. So here is the market entry game, which I showed you in the previous video. So as I said then, player one has 4 strategies, namely, so 2 where they quit, 2 where they continue, and then in each case they can either fight or accommodate. And then notice that in these 2, quit, fight, and quit, accommodate, in both cases, by following the strategy, we go here, and we never use the choice at this node, but this becomes important when we say, talk about 1 deviations and say what would have happened if we had gone this way. Now, player 2, as I said, only has 2 pure strategies because they have to do the same thing at both of these nodes. And so we're going to call these F and A, fight and accommodate. Technically, they are fight, fight, and accommodate, accommodate, but we may as well call it just fight and accommodate. And then we can do the usual thing. We can write down the normal form just by, for every pair of strategies, we just play it out. And so we get this kind of thing. And then at this point, we can stick this into Gambit. Okay. Interestingly, we can now go the other way. Previously, we had a thing where we could turn every extensive form game into a normal form game, but we couldn't go back the other way. But now we have information sets, we can exactly do that. All we have to do is arbitrarily choose an order that the players are going to move in. And then we can set up information sets so that whenever a player makes a choice, they know nothing about what state the game is in. So it's essentially just as though they're choosing simultaneously. So for example, if we take matching pennies, and then we say player 1 moves before player 2, we get this kind of thing where player 1 goes heads or tails, and then in both cases, player 2 goes heads or tails, but player 2 doesn't know what player 1 did. So this is just as good as having them choose simultaneously. And in fact, if we then take the normal form, if we normalize this game, we end up back with the thing we started with, which is matching pennies. And by the way, what this shows is that you can have a game of imperfect information which has no pure strategy Nash equilibrium. I'm going to come back to this point. There's a bit of a subtlety. So there's actually a very big subtlety here, which is there's a big question of what does it actually mean for 2 different games to be the same. And this is actually a very big and difficult question. It's completely outside the scope of this course, but it's kind of it's a simple question to understand. And so what it means for 2 things to be the same can in general be a hard question, and for games it's particularly difficult. So here, these are 2 different ways of turning matching pennies into extensive form. This is the one from the previous slide, and then this is what would happen if player 2 moved before player 1. And there is a strong sense in which we would like to consider these to be the same game, for example. So actually coming up with a kind of precise mathematical definition that captures all of the ways in which we'd like two different games to be considered the same is actually extremely difficult and not really fully solved. So I'm just kind of mentioning this so you're aware of it. Okay. Now, if you remember, every extensive form game in the sense of last week, so an extensive form game of perfect information, as long as it's finite, has at least one subgame perfect equilibrium by backward induction. And because every subgame perfect equilibrium is a pure strategy Nash equilibrium in particular, that means that every finite extensive form game has at least one pure strategy Nash equilibrium. But the example I showed you 2 slides ago, which is this, demonstrates that if we have imperfect information, this is no longer the case. So we can have games of imperfect information that do not have any pure strategy Nash equilibrium, same as for normal form games. On the other hand, as long as our game is finite, as long as our extensive form game is finite, then its normal form is still finite, although potentially much bigger. And so Nash's theorem applies, so it has at least one mixed strategy Nash equilibrium. But note that these can be extremely difficult to calculate because the normal form can be very big.